Today, we are diving into a world you might not think about every day, but it's one that keeps pretty much everything in our modern lives running. We're talking about the microscopic battle against friction that's happening inside every engine, every turbine, really any machine you can think of. And we're going to see how engineers are fighting this invisible war inside a completely digital universe. Let's get into it. It's a massive challenge, right? The space between two pieces of metal moving at incredible speeds, separated by a film of lubricant thinner than a human hair. It's one of the most important and most extreme environments in all of engineering. You can't just, stick a camera in there and see what happens. So what do? How do you see the unseeable?
Well, you build a perfect copy, a digital replica where you're in complete control, you can see absolutely everything, and you can run a million different experiments in a single afternoon without ever picking up a single wrench. Welcome to the world of computational simulation.
But before we jump headfirst into that digital world, let's just quickly set the stage. Why go to all this trouble in the first place? What are the stakes in the real world? Just try to picture the crankshaft in your car's engine, or the huge bearings inside a wind turbine. We're talking about mind-boggling pressures, intense heat, and surfaces just screaming past each other. If there wasn't something there to protect them, they'd literally grind themselves into dust in seconds. And that something is lubrication. This incredibly thin, invisible film of fluid is the only thing standing between a machine running smoothly and total catastrophic failure. So you can imagine understanding exactly how this little film behaves is one of the most critical jobs in engineering. Okay, so if we can't study that film directly, we need a whole new game plan. And this is where modern computing completely changes everything. Engineers build what they call a digital twin. Now, this isn't just some 3D drawing. Oh no, it's a living, breathing, computational model that's designed to behave exactly like its real-world counterpart. Think of it as a virtual laboratory built specifically to study friction. And what's really cool is this slide gives us a peek at the rulebook for this digital world. The physics inside are governed by really powerful mathematical tools, like the Reynolds equation. This thing has been around since the 1880s, but it's the key. It lets engineers calculate all the super important stuff, like the pressure building up in the fluid, how much weight the bearing can handle, and of course, that all-important film thickness. Now, to solve an equation that complex from millions of different points all at once, you're going to need a pretty powerful toolkit of computational methods. So let's take a look at how they actually do it. The basic idea is actually pretty simple. You take a problem that's way too big and complicated to solve all at once, and you just chop it up. You break it down into millions of tiny, simple pieces that a computer can solve one by one. Then you just put all those results back together to see the big picture. It's a process called discretization. And there are two main ways to do this chopping. On one hand, you have the finite element method, or FEM. Think of this like shrink-wrapping a flexible net over an object. It's perfect for seeing how stress and strain affect complex, solid shapes. On the other hand, you have the finite difference or volume method. This is more like laying a rigid grid, like a checkerboard, over a space. It's incredibly good for analyzing how fluids, like our lubricant, flow through that space. So let's start at that big picture macro level. When we want to see how the lubricant is sloshing around inside the entire machine, we need a tool that can handle that kind of large-scale, sometimes chaotic movement. And that tool is called computational fluid dynamics, or CFD. This lets engineers simulate the really complex mix of oil and air, helping them figure out how to get the lubricant exactly where it needs to go. This is how they avoid something called lubricant starvation, which is exactly what it sounds like. It's basically a virtual wind tunnel, but for oil. But what happens when that tiny gap between the surfaces gets vanishingly small? When you're talking about a film of lubricant that's only a few molecules thick, well, at that point, the big picture rules of CFD start to break down. We have to zoom in, way, way in. And that brings us to molecular dynamics. At this level, we're not even simulating a fluid anymore. We are simulating the actual individual atoms and molecules of the lubricant and the metal surfaces themselves. This is the ultimate close-up, and it lets scientists understand the fundamental physics of how friction actually works. Okay, so we've got these incredibly powerful simulation tools, but just seeing what's happening isn't really the end goal, right? The whole point is to create better, more efficient designs. And to do that, engineers have some very, very smart assistants. And this is where artificial intelligence and machine learning come into play. Instead of an engineer trying to guess the next improvement, they let smart algorithms do the heavy lifting. Some of these act like a digital brain, spotting patterns in the simulation data. Others kind of mimic natural evolution, testing and combining the fittest designs over and over to create better and better solutions. And it all comes down to this really powerful loop. First, you simulate a design. Then an AI analyzes the result. Based on that analysis, the AI suggests an optimized version, maybe changing the shape of a tiny groove or tweaking the oil's properties. You simulate that new design, the AI analyzes it again, and the process repeats, maybe thousands of times. It's how you find the absolute best design possible, something you could never do with physical prototypes alone. All right, now for what is arguably the most important step in this whole process, making sure that our perfect digital world actually matches up with the messy, complicated real one. Because, look, no matter how powerful your supercomputer is, its results are really just a hypothesis, and that hypothesis has to be tested. It has to be validated with actual physical experiments. Without that crucial step, all of this is just a very, very expensive video game. And this quote really illustrates the goal perfectly. Throughout the research, you see this happening again and again. In this case, a thermal model from a simulation was checked against real-world temperature measurements, and guess what? The simulation was accurate to within 10%. This is exactly how you build confidence that your digital twin is telling you the truth. And that validation process is not simple. It involves some seriously specialized lab equipment. For example, they use these devices called tribometers. And a tribometer is basically a tiny, incredibly precise machine designed to do just one thing: measure the exact amount of friction between two surfaces. That real-world data is then fed back to make sure the digital world and the real world are perfectly in sync. And that brings us to our final thought. These simulations, these digital twins, are getting better, faster, and more accurate every single day. As they get closer and closer to being a perfect one-to-one match with the physical world, it raises a really fascinating question. At what point does the digital twin stop being just a model and start becoming a reality in its own right?